today's presentation is about a research platform that we've been developing for this project. For this demonstration today, we are going to briefly introduce our reasoning for our approach in developing a research platform and how it will support our project going forward. We will present some of our recent research and then demonstrate how the research team have integrated a research prototype into a working identity system within a sandbox environment. So let's remind ourselves of why we're here. This project aims to support the community in addressing modern challenges associated with digital identity. It aims to provide solutions that advance knowledge and advance technical capacity in addressing these challenges. So while digital technologies are redefining opportunities around the world and governments are embracing digital identity infrastructures, the approaches being taken vary considerably, which leads to uncertainty and incomplete understanding, which can potentially lead to citizen harm. Through this project, we have the opportunity of shaping and guiding these approaches and informed choices in support of a fairer, inclusive world. Well, this project comprises of three key elements as shown here. For this demonstration, we can break this down into taking novel thinking and identifying opportunities for developing technical solutions that can lead to real changes in the implementation of digital identity. To be able to do this, we need a platform on which to develop and to prove these ideas. This undertaking has been a key focus of our engineering team, and its demonstration is the key aim for today. So a research platform provides several opportunities. First, development of such a platform and the hands-on engineering experience it provides supports the identification of strengths and weaknesses of current solutions available to the community. The outcomes of this effort steers research focus and informs community understanding. It also supports research teams in taking their proof of concepts to the next level. Through integration of existing identity frameworks, we can test ideas within environments that mirror real-world implementation to provide tangible results that can influence adoption of innovations. From a high-level example here, using the MOSIP system, you can see that this concept is intended to support the full cycle of research development, including the encapsulation of requirements. It is also expandable to include additional systems, and it should be replicable by other research teams focusing on development of identity systems. So the purpose of today's demonstration is to provide an insight into some of our research and then show how we've integrated a research prototype into implementation of the MOSIP system. In a moment, I'm going to introduce Santosh, who is going to provide a short introduction into our work in anomaly detection and the potential benefits of using autoencoders within the digital identity systems. To follow Santosh, we have Tim and Peter from our engineering team, who will present their recent efforts in developing our current research platform, which will accumulate to a demonstration of Santosh's prototype, which has been integrated into our instantiation of MOSIP in a sandbox environment. So I'm going to pass over now to Santosh, who is a PDRA on our project. Thank you.
Thanks, Mark. Could you please just quickly confirm if the screen share is working perfectly? Thanks, Mark. So I'm going to talk about the research I've been doing into the anomaly detection in identity systems. So this is part of the real-time governance theme of the project. And a simple way to understand what real-time governance is all about is captured through this three-step process, which is detect, understand, and react. So when we talk about detect, we are talking about detecting threats to the system, which we are considering. And So there are two kind of aspects to this whole process. So we have some people working on the threat modeling of identity systems, who are also going through the same process of detect, understand, and react. And what they actually do is that they study the system and then try to understand what are the different threats that are that could be faced by an identity system, and then you would then try to figure out how you would react to it, which may be, for example, making modifications to how the system is developed so that it can be made more robust. However, there can be threats that we have never seen before, and therefore, difficult to foresee such, unseen or unknown threats. And this is exactly where anomaly detection comes in, where we want to build the capability to detect these kind of unknown threats, and then we would proceed to, understanding these threats better and why they were, what are the origin of these anomalies, and then we can then figure out how to act on these detected anomalies, which could be some manual intervention based on the actual understanding that we have. So what are anomalies? Anomalies are rare events or data points that differ significantly from the rest of the data. Now we have three different types of anomalies, starting with a point anomaly, which is a single data point. For example, like a fraudulent credit card transaction. Now, this single transaction might be anomalous, for example, due to an unusually large transaction amount. Now, you also have contextual anomalies, which are also pointing to a single data point. However, they are anomalous due to the context they were observed in. For example, if we are tracking the daily temperatures of a city, for example, London, and then you observe a day in which you record 30 degrees Celsius in the month of December, then that would be an example of a contextual anomaly. We also have collective anomalies, which is not an individual data point, but a set of data points together that can be considered anomalous. So, for example, if someone makes multiple ATM withdrawals in a short period of time, then collectively they can be considered as an anomaly. So anomaly detection is not new. It's been used in a bunch of different real world applications. For example, in intrusion detection, so which is the task of detecting unauthorized access in computer networks. We've also already given an example of fraud detection, and also a number of other applications where the same principle of detecting anomalous events has been applied. Now, our main focus is on identity systems, and we hope to, build on the knowledge that we have already that's already out there by solving very related problems. Now, moving on to the kind of methods we can use for anomaly detection. So when we're talking about machine learning methods, based on the availability of labels as normal or anomalous, we have two basic categories of machine learning approaches. So you have unsupervised methods that work on unlabeled data. So imagine you don't have labels, but you still want to detect anomalies. You would use an unsupervised method, which works under the basic assumption that majority of the cases in your data are normal. And this is also kind of synonymous with outlier detection in this case. And this picture on the right top gives you an example of how such a method would occur, right? So the idea is to create boundaries around the highly dense regions of the data, and the rest would be detected as anomalous. Now, if we have labels for the data points as being normal or anomalous, then you would use a supervised method, which will train a classifier, which basically tries to create a separation between the two kinds of data points. So some examples of supervised methods might be familiar to most of us, like logistic regression or random forest, and so on. But there are certain challenges in using either of these kind of methods in our application. So the first challenge is that the lack of availability of labeled data in applications like ID systems make the supervised learning approach infeasible. And even the unsupervised methods are, as it is, are not so appropriate to be used as it is, because they are likely to detect anomalies that are not relevant, right? This figure here is to kind of give you an example of that, example of the case that not all outliers are anomalies. So it all depends on the actual application we are working on, where for example, in this data set for illustration, we have this cluster of data points which is quite far away from the majority of the data. However, the true labels for these data points, if you observe this cluster of data points, are not anomalous, or in this case, because this data set originates from fraudulent transactions, these are actually not fraudulent. So therefore, we cannot just use unsupervised methods as it is, even though we don't have labels. So what can we do then? So what we propose is to use a semi-supervised approach, which can also be thought of as novelty detection, which works under the assumption that we have some number of verified genuine events that are available for us to train our models. So I think these 4 points kind of summarize what the semi-supervised approach is all about. So we have training data that is not polluted by anomalies, so which is exclusively normal or genuine events. And what we can then do is we can use our unsupervised methods to create a tight decision boundary around these genuine events. And then the idea is that anything that any new data point that comes in which falls outside this boundary that we have learned would be detected as a novelty, right? So the novelty comes in, the word novelty comes from the fact that this is something that we have, it's different to something that we have observed before, or something that we expect to be normal. So that's why we refer to these as novelties as well. And one of the key advantages of using such a method is that these methods will be robust to change in anomalous behavior, because we are not assuming any knowledge about the nature of anomalies, and therefore they can be quite robust. So this picture on the right side is a bit complex, but it actually captures all of these 4 points that I just walked through. So before you train the models, what you have available to you are these white data points. And then the model learns to create a decision boundary. Not only does it learn this red boundary, it also creates these nice contours around the whole data space, which actually tells you how likely a data point is to be anomalous. So for example, these lighter shaded regions, if a new data point comes in, then they are extremely likely to be anomalous compared to a darker shade of blue over here. And these are just the true labels of new unobserved data points that we see how they almost all of the yellow points have been are lying outside the boundary, showing how these models would work. All right, so let's now discuss the different types of algorithms that we can use for such a task. So here I want to make a distinction between 2 general categories of methods. I'm calling them the shallow and deep methods. So an example of a shallow method is the isolation forest algorithm. And the isolation forest works by randomly partitioning the data to isolate each event. And the idea is that anomalies are detected because these are the data points that require the fewest number of partitions to isolate them. And this is exactly what is illustrated in this diagram. The blue data point xi is is normal or genuine, and you can see because it's lying deep into a dense area of data points, it requires a lot of partitions to isolate such a point. Whereas this example xo, it requires very few partitions to isolate it. So one of the things you will notice here is that these partitions are generated directly on the raw data space without any transformations. Now, on the other hand, you have methods like the autoencoder, which is a deep learning based method, which work in a completely different way. So how does an autoencoder work, right? So an autoencoder has two components. The first one is an encoder, which compresses the original data, the input, into a compressed form, right? So you can think of this as compressing a file on your computer. So it basically reduces the data to its essentials. And then the decoder tries to reconstruct the original input starting from this compressed point. Now, the idea is that if you train this model on exclusively genuine events, then the model is going to learn how to reconstruct these genuine events with very high accuracy. And because the anomalies are going to be somehow fundamentally different from your genuine events, the algorithm will really struggle to reconstruct these anomalies very well. And so, any data point that has a high reconstruction error between the reconstructed output and the original input can therefore be detected as an anomaly. So the images here is just to illustrate how this compression works, because usually your input is going to be complex and high dimensional. So it could be a 3D image of this mushroom. And what you have after this encoder kind of transforms this data, where the data goes through these multiple layers of transformation, which is where this word deep comes in, because it goes through these multiple layers of deep networks. And then what you would have is almost just like a wireframe of what you start with, which is just the essential representation of the originally complex data. All right, so when do we want to use these kind of deep learning based methods, right? So the autoencoders, for example, they work better than the isolation forest when the underlying phenomena that generated the data is complex. So most real world applications kind of fall into this domain where you have a lot of richness in the data with a lot of high dimensions as well. And that is the second point, where autoencoders also work really well when the data is high dimensional, and many of the features require nonlinear transformation before we can identify the decision boundary to separate the classes. Okay, so we have different kinds of methods, like you have shallow methods, we have deep methods, and what we then wanted to do was we wanted to test these different methods on a real world data set. Of course, we don't have a real world data from an identity system, so we decided to test these methods on a data set of credit card transactions, where we have labels for whether each transaction were fraudulent or not. But because our aim was to test how a supervised, semi-supervised method would work, we actually, went through the same process where, for training our models, we removed all of the anomalous events from our training data. So we used just a subset of the genuine events for training, using which all of the different methods would try to create a boundary around these training genuine events. And then finally, we also have a set of data points to test the performance on, which contains both types of events. So what we ideally expect to observe is that the model would actually would output a higher probability for these green points to be anomalous, and would actually give very low probabilities of being anomalous for the brown points. So let's actually see how these models work. So this is a precision recall curve that is a typical performance measure for evaluating the performance of different models for this kind of a classification task. So if you're not really very familiar with this curve, there is typically a very strong trade-off between precision and recall. So on one end, you have this region where you have high precision and low recall, which is basically telling you that the model is trying to minimize the false positives. Okay, so the idea is that whatever events that the model is actually predicting as anomalous, the vast majority of them are actually truly anomalous. Whereas on the other end of the spectrum, you have a low precision but high recall, which basically means that of all the data points that are truly anomalous in your data set, the model has managed to predict most of them, as in detected. But this usually always happens at the cost of precision, which results in a lot of false positives. So whether you want to penalize false negatives more or false positives more is a completely a business decision, and which is why this graph is ideal, because this graph actually evaluates the performance of all of the models for all levels of precision and recall. So basically, if you look at the region which is close with a recall closer to 0, this means that you would like to minimize false positives, and you see even in this region the autoencoder is the one that is doing really well, and even on the regions towards the the complete recall, as in a recall equal to 1, you still have the autoencoder edging all of the other models. So yeah, so the bottom line is that you see that the autoencoder is actually the best performing model, and the numbers that you see on the legend, even other than just eyeballing it, what a way to quantify the performance of the model would be to calculate the area under each of these curves, and this is exactly what you see here. And you see that the autoencoder indeed has the largest area under the curve, and therefore the best performing model over a wide range of business decisions that you might want to use these models under. Now, to get a flavor of how these models actually worked on the data, here we are visualizing them in just 2 dimensions. So earlier I mentioned that there was this cluster that was wide away from the data points that actually indeed is not anomalous, right? So if you see among all the 4 models where you have the autoencoder on the bottom right corner, it is actually the only model that is having this cluster that is far away from the majority of the points within the boundary. So even in 2 dimensions, you can see how actually the autoencoder is such a superior model compared to the other 3. So just to summarize what I've spoken about, so we've developed a semi-supervised approach for anomaly detection that is suitable for identity systems, where you have anomalies that are unknown and potentially could also change over time. We've also provided evidence that show that deep learning methods like autoencoders indeed perform better in complex, multidimensional real-world data. And now I'm going to pass on to the rec team that will now demonstrate how they have utilized this piece of work to implement anomaly detection within the MOSIP system. Thank you.
My name is Tim Hobson from the Turing Research Engineering Group, and today we're going to talk about a piece of work we've been doing developing real-time data analytics on top of a digital identity system. And I'm going to talk probably for about 20 minutes, but with the help of my colleague Peter Foster, who's also in the research engineering group. And this is a piece of work that has been a collaboration with Santosh, who I think you've heard from. So the overall approach is one of tactical intervention. That's the sort of project level approach. We're not attempting to develop identity systems from scratch. Instead, we want to intervene. We want to add intelligence or data analytic capability to enhance existing digital identity systems. Specifically, we're aiming to enhance the real-time governance capabilities. And in fact, this intervention that we're talking about today is all about anomaly detection. So we're going to demonstrate this piece of work, which is really a prototype. It's a sort of proof of concept where we're integrating an anomaly detection model into an existing identity system. We've also implemented a pipeline for generating synthetic data and then evaluating the performance of the anomaly detection. And then we've got a kind of an end-to-end demonstration with a customized reporting user interface. So first, just to introduce the sort of top level, high level sort of design structure. So we've identified these are the key components, the essential elements that we need to develop such an intervention. First of all, we need a running instance of some digital identity software, which we refer to as a sandbox. It's a sort of testbed area where we can develop, we can interact with an existing system, and that's something we're going to take, if you like, off the shelf. We're not going to try to build from scratch. But that sandbox instance alone is not useful without some data actually flowing through it. So we need a mechanism to generate data. We're constrained, of course, by the sensitivity and the privacy aspect of data in real world digital identity systems. And so we're obliged to look to simulation to generate synthetic data that we can push through the sandbox system. And then the next piece we need is the analytics engine. We need to be able to access data from that sandbox and process it, and in that way gain insight. And then we need to communicate those results. In this case, to a system administrator or through some kind of reporting mechanism. There is an alternative route, which is sort of a feedback from the analytics engine back into the sandbox directly. So that would be a data-driven intervention, which actually affects the operation of the sandbox itself in real time. We're not going to demonstrate that right now today, but that's something else we're interested in considering. So that's the high level design, if you like. From now on, we're going to concentrate on real-time governance within a particular identity system, which is going to be MOSIP, of course, partners of the project. So we're interested in working with the MOSIP digital identity platform, and we're going to demonstrate our prototype intervention using that system. So the first element we needed was a sandbox instance, and we have such a thing for the case of MOSIP running in the cloud. It's a complicated design, which I'm not going to try to describe in detail. The sort of the important aspect is really to understand from a functional perspective what functions can be performed given this sandbox instance. And really, there are three functions that are supported by the MOSIP sandbox. The first is a pre-registration step, which is the user's initial interaction with the digital ID system, where they first enter some information about them and sort of kick off the registration process. The second step is the full registration, where they actually submit additional data, including biometrics, and then the third process that is supported is that of authentication, where the user can authenticate against their own registered identity. So at this point, I'm going to hand over to Peter, who's going to describe the pre-registration process in a bit more detail and talk about how we're interacting with it and introducing our anomaly detection model.
Thank you, Jim. So to provide you a bit of additional information on the pre-registration. So the pre-registration is a process that users need to complete before they subsequently register in person at a registration center. And therefore the pre-registration involves gathering of a certain amount of demographic information, and it also involves the user selecting a registration center and booking an appointment at the registration center. So what this essentially involves is the user navigating via a web interface, and the best way to show you is to demonstrate that. So what we see here is a video of a user navigating through the pre-registration process via the web interface. The first step involves authentication, so this is done using an email address or using a mobile phone number. And the next step is to enter the demographic information. And so there's a form for this. The user enters the demographic information by the form. And I'll come back to this shortly, but what you actually see is a simulation of a user entering their information. So in a typical situation, what we would expect is that the user navigates from field to field. They might pause at a given moment and continue by the form. So that's essentially what you see here. This is a simulation of a user navigating the pre-registration process. After the demographic information entry, the user navigates to the next step in the pre-registration, which you see now, which is to upload supporting documentation. So what this involves typically is the user selecting from their machine a PDF scan of a passport or similar documentation and uploading that documentation. And once they've done that, the next step is a confirmation dialogue, so that they see and can verify the information that they've entered. After they've verified that, they proceed to the next step, which is to book an appointment at a registration center. So this is what you see now. The user is required to select a registration center, and then in the final dialogue of the pre-registration process, they are required to select a registration slot. So this is a time that they book to appear at the registration center and to complete the registration. So this is what you see now, the user selecting a slot for the registration. And once they click continue, they receive a confirmation that the registration has been completed successfully. Next slide, please. So at this point, I'd like to move on to our research proof of concept. So what we're talking about here is the detection of anomalies in the pre-registration process. So for this purpose, we assume a threat model where an attacker intends to complete the pre-registration in automated fashion, but they do so in a relatively unsophisticated way using a bot which simply enters the fields and navigates through the pre-registration process via the web interface. but without any delay that we typically expect for a human user and human behavior. So our anomaly detection pipeline looks as follows. We are interested in characterizing unusualness of behavior, and we do this by the timings that are between the successive pre-registration events. So in the MOSIP system, we have events which happen as the pre-registration process occurs, and based on these timing information events, we then attempt to classify sessions using a model which has been pre-checked. So this is an anomaly detection model, which is based on timing information. And then we use that model to display a score, which is done using an interface and a dashboard, which we'll come back to shortly. Next slide, please. So to describe to you how we've achieved this, we have implemented functionality which centers around simulating the pre-registration process. So this is what you already saw, but it needs to account for the fact that we have the potential normal user versus the anomalous user. The anomalous user being the one that is the attacker attempting to navigate via the pre-registration process using an unsophisticated bot method. Now, there are two methods to simulating pre-registrations, which we implement. One is via the so-called MOSIP packet utility, and the alternative approach, which you saw in the preceding video, is to use a web browser and to interact with that web browser using the Selenium API. So that's how we've implemented it. We use the Selenium API to initiate commands to the web browser. So this is done in a browser agnostic fashion. It works for Firefox, Chrome, to name a few. And that is then an automated process which we simulate. And the simulation is done using a random process. So we have a simulation for a normal user versus the anomalous user. And in this way, we generate normal versus anomalous pre-registrations and submit them to the MOSIP system. So the best way to show you, again, is to demonstrate that using a video. So what we see here is an example of an anomalous user as per our threat model. So the anomalous user, as mentioned, is using a relatively unsophisticated method for entering the data, navigating from field to field. And as you can see, the pre-registration happens relatively quickly. So in our simulated anomalous pre-registration, we would expect the timings between the successive events during pre-registration to be relatively short, and that's what we then subsequently characterize using our anomaly detection model. So at this point, I'd like to pass back to Tim, who will tell you more about how we've implemented the dashboard and the data engineering side of things.
Thanks, thank you, Peter. Okay, so just going back to our sort of high-level model, we've now described the first two of the kind of essential elements. We've got the sandbox up and running, we've got the data simulated, and the next step is to actually be able to analyze it. And for this, we integrate with another piece of MOSIP software. It's distinct from the sandbox. It's a reporting framework which can be pointed at any running instance, whether it's a sandbox or a production instance of MOSIP, and it can be used. It's designed for reporting based on the data inside the system. So what we have, again, this is relatively complicated. I'll just sort of try and simplify it. There's a main database within the sandbox that is obviously updated when the pre-registration process or any other process takes place. There's a data stream, real-time stream processing pipeline. Essentially, the database is continuously being watched by some software which will then propagate any changes in the data into the analytics engine, which is a Spark cluster, and the output of that analysis can be pushed to an elastic search data store from which it can then be pulled and visualized in the form of a dashboard. So this is the mechanism we're using, and of course our anomaly detection code will reside as a Spark job in the Spark cluster. So this just lists some of the kind of the engineering steps involved in getting this prototype up and running. I'll show you the reporting piece, which is the only bit that you haven't seen up to now, I think, in a moment. I guess it's worth emphasizing just the amount of data engineering involved in just in putting all these pieces together from the data from the simulation, and embedding training and calibrating the model, and then make the plumbing involved in getting the data through the model and then pushed to the output and the reporting. So what I can do now, I think, is to sort of demonstrate the end-to-end system. This is the web interface that you're now familiar with, but what I want you to imagine now is that there are many different users all interacting in parallel with pre-registration sessions in their browser. So currently there are many different client machines all being interacted with to generate this demonstration. And the kind of the other end of the pipeline is this dashboard which displays the results of the model. So in the top left, you can see each individual pre-registration event shows up in this blue bar in the chart. Below that, you can see completed sessions, which are characterized as either regular or anomalous, based on the classification that the model assigns. Underneath that, there's a log of data where you can drill down into sort of the details of the metadata that are being processed. And then on the right-hand side, you can see the statistical visualizations associated with the classification model. We've got a histogram of the scoring, so the model outputs a score in the unit interval, and those at the above a certain threshold are considered anomalous, and then below that we can actually see the histograms of actual event times for the different steps within the pre-registration process, and so you can actually visually see the distinction between the regular versus the anomalous behavior. So to summarize, then we've established a sort of generic model for intervening in the digital identity system to perform sort of intelligent data analytics, and we've implemented like a simple proof of concept of that model, which aims to detect anomalous user behavior in the pre-registration process within MOSIP. We've integrated that within the reporting framework so that we can actually perform the analytics and report the results. And a big part is also around synthetic data generation, because again we're constrained in our use of data. Real world data is of course highly sensitive, and we don't have access directly. So what's really kind of exciting, I guess, about this is the sort of foundation that it lays for for data-driven interventions that we can now iteratively develop to enhance the real-time governance capabilities within MOSIP in particular. This is the first of a deliberately simplified if you like, a deliberately simplified threat that we're simulating for the purpose of this data engineering effort. Now that we have that in place, we can now iterate and develop more sophisticated schemes. And we're also producing a technical guide, a working with MOSIP sort of handbook for other research teams that are working with the same system. So looking forward then, a few of the next steps that we're taking to take this work forward. The thing we're really keen to refine is the sophistication of the threat model that we're working with. We've deliberately chosen a simplistic model to start with in order to get a first proof of concept running. But we're now engaging in a comprehensive threat modeling exercise, specifically focused on MOSIP and the MOSIP system and data model, and this will include consideration of not only the pre-registration, but the registration process and the authentication processes, which are realistically more likely to be attacked. Inevitably, this scales up the dimensionality of the classification features that we want to analyze. This is very interesting from the research perspective. The autoencoder model that we're using to identify anomalies is expected to perform particularly well in a high-dimensional setting. We also are, in hand with that, will go more realistic techniques for data synthesis. That threat modeling exercise will inform the data synthesis regime that we then sort of implement and take forward. And finally, we'll need actually to be able to automatically calibrate our system when we come to deploy it in production. Again, because we don't have access to the data within a live system, so we're calibrating and training sort of offline using more curated data. In practice, we'll actually need to be able to need to make the system intelligent enough to sort of calibrate itself once deployed on the real live data that we can't access. And so that's a final piece that we'll be taking forward in the near future. And that completes the demonstration. Thanks very much for listening.